Hello students, welcome to MyAbhyas. My name is Sahana KS and I am your physics educator. So till last session we have explained you about the heating effects and also the Joule's law. But today we will be deriving the Joule's law of heating. Okay, so today's goal is set, that is we will be having this Joule's law of heating concept derivation, and also we will be learning about a concept which is called as electric power, which is a small concept. And this comes you can learn this electric power concept in Joule's law of heating itself while deriving. So this derivation, whatever is there, this is very important for you people because this will be asked compulsorily in your exams from this chapter. Clear? So coming to the derivation, we'll look into it. So yesterday I had explained you the heating effects of electric current. So what happens generally? Whenever you just switch on the iron gets hot. Whenever you switch on the electric heater, the heater also, like, it warms up the water, right? So this is what is happening there. Here the electrical energy is getting converted into heat energy. So what is the reason behind that? Okay, so these are the instruments which are meant to convert electrical into heat. But now what I want is, why heat is liberating in some of the apparatus like refrigerator, okay, the walls of the refrigerator. So what is happening there? Why is the bulb, okay, when it is switched on for a longer time, it is getting hot? Okay, so yesterday we got the reason why. Because when I consider a conductor, so if I consider one conductor, for example, if I take this, okay, so then I'll connect it to a certain battery of certain potential. So this battery is connected here and the current starts moving, right? So that time what happens, that is, the electrons flow starts. Then because this is positive, here what happens, the positive potential lands up, and whatever electrons are there in this conductor, they tend to move towards this positive potential. So because of while these electrons are moving near positive potential, what is happening? These electrons collide with each other. Because of the collision, the energy whatever is taken from the battery is being released, and because of the release of that heat energy, that is, or the because of the release of the extra energy, what is happening, the heat is getting liberated. Clear? So that is the exact process what is happening. Because of the collision of electrons towards the walls of a conductor or in between them, what is happening, the energy is getting released. So which type of energy is getting released? The heat energy is getting released. So this is how the heating effect is effective. So now we'll derive. Okay, we'll just take a circuit diagram like an ideal circuit, okay, and we'll derive the equation for the heating effect. And also yesterday I had explained you, that is in the last session I had explained you about the heating effect on which it is dependent, right? So on what it is dependent? So the heating or the heat is directly proportional to the resistance of that conductor, okay, and also it is directly proportional to what? The time, and it is also directly proportional to the square of the distance, right? Sorry, square of the current. So this three including, what do I get? I get an equation H is equal to I square R and T. So this is a theoretical study for me now, because H is directly proportional to R, yes, because resistance increases, heat increases. How is resistance increasing? If the collision is more, okay, if the collision is more, that time what is happening, the resistance offered by the electrons also will be more, so heat increases. Next, the time, because if the flow is high and much of the electrons are colliding, if the energy given is high and the much electrons are colliding, then the heat increases. And also because of the current. See, here what happens is, I have electrons in the conductor, free electrons I have, but also what I am doing, I am giving it some energy. So as I am giving it some energy, what is happening? These electrons are moving very rapidly, okay, because they receive external energy there in terms of the battery. So as it moves, again what I will do is, I will put some electrons again. So the time what happens, there will be overload of electrons. As there is overload of electrons, the collisions become more. As the collision becomes more, what happens? The heat is liberated more. So H will be directly proportional to the square of the current. So this thing we'll be deriving it so that you people can derive the equation step by step, and you have to remember that the equations whatever you write down, okay, please remember those equations. Consideration and other factors you can easily do it while you are doing the circuit or drawing the circuit. So coming to the first, what I have to do is I have to draw a circuit, because to write the consideration means it will be the introduction. So to write that, I need the consideration. So before that, what I'll do is I'll just take the circuit, ideal circuit. So now what I have to do is I have to take a conductor or a resistance wire I will take. Then I have to take the potential difference V. I have to take a battery, I have to take an ammeter, and I have to take a key. So why should I take this? To prove that the heat is equal to the square of the current. It is also equal to the resistance and also the time. Okay, so to know that, first I'll draw the circuit. Please concentrate because this is very important. So first, as usual, an ideal circuit you have to take. So there will be a battery, there will be a key. Clear? Next. So here I'll take a resistance wire, and then here the ammeter which measures the current. So this is my battery. This is the way the electrons flow, and this is nothing but it is R. This is K. This is plus and minus. This is an ammeter, and to the parallel to this resistance wire, I connect a voltmeter to know the potential difference. Okay, so this and this point I took it as X and Y. Clear? So this is my circuit to find out or to prove the Joule's law of heating. Now here what is happening is I have a ammeter placed in series with the resistance wire and voltmeter placed in parallel with the resistance wire. I think you people know that whatever fuse in your home is connected, it is a series connection, because to avoid more number of damages to the apparatus and also electrical appliances, that will be connected in series, and that is why sometimes when the overload is more, the fuse breaks out, because it will be made up of usually copper in previous days, but nowadays they are using alloys. Okay, what are alloys? Alloys are nothing but they are a mixture of two metals. So what happens is that melts and there won't be any power supply. So that is how fuse breakout happens. So that will be in series connection only. Okay, in series connection only. That is why every time whenever you are measuring the current, you will be placing the ammeter or anything which measures current in series. Okay, and whenever you are measuring the potential difference, you take it always in the parallel. Clear? So now consideration. Consider a battery, okay, connected to a resistance wire R, and then parallelly connected to a voltmeter V, and also with the ammeter in series in A. Okay, so now what I have to find out is I have to find out the H. Okay, that is the heating effect, or what is the heat liberated. I have to ask that. I have to find out that from this circuit. So now I have three definitions. Okay, main three definitions I have, which we have studied earlier. Okay, in some sessions we have, in the first session I think we have studied, in the second also we have studied. So what is that? First thing is, what is voltage or potential difference, right? And what is current? And also what is resistance? So what is a voltage or a potential difference? Okay, so it is nothing but it is the work done in bringing a positive charge or a charge from infinity to a prescribed point. So what is happening? I have given you the example here that if there is a point P here, and if I have to bring it near A, what I have to do, there is a charge Q, then this charge I have to bring it to point A. So here what happens, the work has to be done. So I have to bring this Q to A. So for that work has to be done. So if it is like, if the charge is positive and if there is a other charge here, or if the positive charge, I have to bring it to point A. And if this is in the lower potential area and if this is in the higher potential area, what happens is I have to do more work. Okay, I gave you an example of water pump where if you have to flow water from up to down, it is easy. Okay, you can just connect a pipe, it comes because of the gravitation. But what you have to do is, if you have to take the water from the sump to the other tank, upper tank, what we have to do is, we have to put a motor. Why? Because of the external energy, right? So when I give that external energy only, water pumps upwards. So there what I am doing, I am giving extra energy there. Okay, so same thing here. So what I am doing is, for the potential difference, or what is potential? It is nothing but it is the work done in bringing the charge from certain point to a certain point. Okay, or from infinity to a certain point, we call it as the potential difference. So keep in mind that definition. Next one is current, the rate of flow of charges, we call it as current. And next one is resistance. It is the opposition offered for the flow of electrons. So that is also a resistance. So these three factors now will be coming here for the existence. So this work, okay, this work needs some power. I am giving some external energy or external power, right? See here, for example, if I take a battery here, then what is happening? This resistance has certain resistance, okay, and also it has certain electrons also, okay. So what happens when I just move it here, that time it offers the current some opposition, okay, but some electrons which are high and some which have more energy, that they can escape it. But now what I am doing here is, this battery, with this battery I am giving extra energy. So extra energy means extra power, right? For example, if there are two people standing, one is when there is 5 kgs of huge stones. So as 5 kgs is there, one man cannot lift it, but the other man can lift it till the head. So that time what you will say? You will say the other man, that is man B, has a lot of strength, has a lot of power, right? So in the similar way, what is this work I am doing? I am giving certain power to that, so that this charge can come to that point. So that work, okay, I will be taking it in terms of power. Okay, so power is equal to what? It is nothing but it is the product, or it is nothing but the product of potential difference and current. Okay, so V into I is nothing but the expression for electric power. So what I can say is, in the first expression, electric power, okay, or the power absorbed by the you can say resistance wire is equal to, that is P is equal to V into I. Okay, so after this, what I have to do? I have a problem with I, okay, and V I'll keep it as it is for now. So what is I factor, or what is the formula for I have? It is nothing but V into Q divided by T, right? So how did I get this? Nothing. It is the formula for current, right? I is equal to Q by T. The rate of flow of charges is nothing but electric current. So I have substituted. So in the next case, what I will do? So in the next case, I have to know what is heat energy. Okay, how much heat is liberated? How is it getting liberated? Okay, so what I'll do is, for this charge to be coming here from low potential to high potential, it is taking some time. So here, as the electrons are moving, okay, in this circuit, as the electrons are moving, it is directly or indirectly dependent on time, because I have said you Q divided by T. Q divided by T means how much charges are moving in certain time. That is the rate of flow, we say, right? Rate of flow of charges. So I have to take the count of time. So now what I do is, I'll take another factor here. So that is equal to V I into T. So take this as first equation and this as second equation. So why did I put I? Okay, V into I is similar.